You remember that last time we said that during biochemical reactions, enzymes can reduce the activation energy associated with the formation of products from reactants, and that as a result, enzymes can affect the rate of reactions. We want to discuss how to analyze this mathematically in a formal sense today, and to do that we are going to return to these folks shown here, Leonore Makaylas and Maud Menton. They developed a way to analyze biochemical reactions, making some assumptions about how we go from reactants to products, and then based on measurements of actual rates using various known concentrations of substrates, how one can characterize the kinetics of an enzyme during a biochemical reaction. And the Makaylas-Menton theory of enzyme action works basically in this way. We assume that an enzyme E and a substrate S interact, and that they need to form a stable temporary complex, and that occurs with a rate which we'll call K1. That complex can also fall apart, and so there's a backwards rate constant called K2. That enzyme substrate complex is a metastable state, and the interaction of the substrate and the enzyme is required for the enzyme to catalyze the formation of products from the substrate. So once we have one of these metastable complexes, it can proceed to the formation of a product. And you remember that an enzyme is neither created nor destroyed in these reactions, and so at the end of the day we have the enzyme back out of this process plus a product, P. And we can assume that that forward reaction has a rate constant which we'll call K3, but it can also be true that the enzyme and product can go backwards to form an enzyme substrate metastable state. Now, the Makaylas-Menton theory, which seems to fit a lot of enzymes, makes some assumptions about what's going on here. And what are those? Well, first of all, the formation of the metastable enzyme substrate complex is very fast compared to the decay of that metastable complex to enzyme plus product, which is assumed to be much slower. And this actually turns out to be a good assumption for most enzymes. Secondly, that final constant K4 we assume to be negligible. In other words, once that metastable state gets converted to a product and the enzyme is released, it's very, very hard to go backwards. In essence, this is an irreversible reaction. And that seems to be a pretty good assumption as well. So if you take a biochemistry class, you'll learn a lot more about the mathematics here. There's even a end of the chapter problem in World of the Cell that allows you to derive the formula here for Makaylas-Menton enzyme kinetics. We're not going to do that here. Instead, we're going to use this formal kind of analysis to try to understand the basic properties of an enzyme. You'll learn a lot more about this as well if you're in the 304 lab course. It turns out for Makaylas-Menton kinetics that if one analyzes the relationship between the substrate concentration and the velocity, the rapidity of the reaction, that one gets this kind of asymptotic curve in which, as we go to very high substrate concentrations, the rate of the reaction sort of levels off. This allows us at the top of the graph here to define, as you see by the dotted green line, a maximum velocity for the reaction, or Vmax. In addition, the mathematical formalism of the Makaylas-Menton equation allows us to relate Vmax, the substrate concentration, and a constant which we'll call Km. And you can see that that equation is there in the middle of the graph. All right, so what's going on here? Well, Vmax we've said is the maximum reaction velocity given a certain concentration of enzyme in which we're measuring the reaction rate. And it assumes prevailing conditions, the pH, temperature, things like that. We've seen that those can affect enzyme function. Okay, that's pretty straightforward. What about this other thing, Km? Well, Km is an intrinsic property of the enzyme under the given conditions. And we can measure that, as we'll see in a moment. Now, sometimes people will tell you that Km measures the affinity for the substrate, and certainly substrate affinity is part of what's going on with Km, but it's also Km also involves the rapidity with which substrate is converted to product. So it measures how quickly an enzyme and substrate can get together, but then once they're together, how fast they can make product. And those are kind of wrapped up together in this constant Km. All right, so that's basically what these two mean. And let's look at some situations along this graph that help us to understand functionally what Km means in terms of what an enzyme is doing. So in the first case, let's consider the left part of the graph. In this region of the graph, the substrate concentration is very much less than the Km. In this case, we can make a simplifying assumption that the denominator of the term for the reaction velocity, we can kind of ignore that S is down there, and so the denominator basically becomes Km. And so this boils down to the velocity in this part of the curve is Vmax times the substrate concentration over Km. In other words, there's a linear relationship between increasing substrate concentration and the velocity of the reaction. So we can think of this as enzymes floating around in a tube if we're doing this assay in a test tube. And there are plenty of enzyme proteins kicking around. But because there are very few substrates, the enzymes are essentially waiting for an encounter with a substrate. So they are bouncing around waiting for the substrate molecule to interact with them. So if we give more substrate molecules, the likelihood of that interaction will increase. And so the rate at which individual substrate molecules will be converted to product by the enzyme will increase in a corresponding fashion. Okay, so that's one case. Now let's go to the other extreme. Let's go up to the top of the curve here. In this case, you can see that the reaction velocity is leveled off and is asymptotically approaching Vmax. In this case, the substrate concentration is vastly greater than Km. And if you look at the algebra here, then you can simplify this by saying that because S is so much greater than Km, we can kind of ignore Km in the denominator. And now we get Vmax times S over S. Well, the S's cancel, and so now the reaction velocity is basically equivalent to Vmax. In this region of the curve, there's so much substrate that there's an absolute glut of substrate, and so the enzyme is each enzyme is working as fast as it can, and in fact, substrates are waiting in line in order to be converted to product. You can think of a revolving door in an office building. Those revolving doors, they limit the rate at which the reaction can occur, and at this point, there's a maximum number of people that you can cram into a revolving door at any given time, and that's basically what's happening here. There's so much substrate around that the enzymes are simply overwhelmed, and so the reaction velocity approaches this maximum Vmax. Right, there's a third case, very special and important case we want to consider, and it provides a direct relationship between Km and Vmax. And that's case number 3. When the substrate concentration exactly equals Km, the Makaylas constant, then the velocity of the reaction is roughly equal to Vmax over 2. And you can do the algebra after class sometime to show that that's the case. So now we have an intuitive understanding of what Km is. Km is the substrate concentration at which the velocity is 1/2 of Vmax. And this then allows us, if we know Vmax, and we know the substrate concentration at any given point along this curve, to actually calculate Km for a given enzymatic reaction. Now, if you take 304 lab, or maybe you've done this in another biology course, I know I did this when I was a teaching assistant at Berkeley in an introductory biology course at UC Berkeley. You can measure Km and Vmax in the following way. we can take the Makaylas-Menten kinetics and we can actually generate something called a Lineweaverburk plot. The Makaylas-Menten curve is an asymptotic curve, and it's sort of hard to calculate things from that. But it turns out if we take the reciprocal of the velocity and the reciprocal of the substrate concentration, this curve is transformed into a straight line. And that's very nice for making calculations. So that's what you see here. In a Lineweaverburk plot, the x-intercept and the y-intercept tell us what we need to know about Km and Vmax. Because we're taking the reciprocal of both the x and the y variables, this is called a double reciprocal plot. And so in the case shown here, we can take that plot, as we'll see, in an experiment, transform it into a Lineweaverburk plot, and that allows us to make our calculations directly off of the graph. So here's an example from your textbook. This is figure 12 from World of the Cell. And it shows measurements of enzyme kinetics for an enzyme that's interacting with glucose. So in each of the tubes, we're putting in progressively larger amounts of glucose. As you see, the millimolarity is given for each of the tubes. And we're going to measure the initial reaction velocity by detecting the development of a color product in each of the tubes. The darker the color, the more substrate has been turned into product. And there are other ways to measure this initial reaction velocity, but a lot of them do involve these colored reaction products, which can be measured in a spectrophotometer. So we can do this for an enzyme that acts upon glucose and generates a colored reaction product. And you can see that we need a blank, that's the thing on the upper left, where there is no glucose, and so we better hope that we get a zero initial reaction velocity out of that test tube, and the B stands for blank. And then we're upping the concentration of glucose progressively and measuring the color as an indirect measure of reaction velocity. So if you do this for a typical enzyme, you'll get an asymptotic curve, just like the Makaylas-Menten kinetics would predict. And you see the curve plotted there in figure 6.12. Now, it's hard to measure things straight off the curve, but you can kind of get a sense for where Vmax is going to be, maybe about 8 micromole per minute, let's say, at the top of the graph. And so you can get a sense for where 1/2 Vmax would be. And so you can go down to where 1/2 Vmax would be, say about 3.7 micromole per minute. And then you can go over to the curve until you hit the curve, and then go down until you hit the x-axis. And that will roughly tell you what the substrate concentration is at which we're at 1/2 of Vmax. And that, of course, is the Makaylas constant Km. But again, it's hard from a curve like this, so let's do a double reciprocal plot, which is figure 6.13 from the same example. So now, because it's a double reciprocal plot, the most dilute glucose and the slowest reaction kinetics, or velocity, are on the upper right of this graph. So everything's sort of flipped upside down. So we can take that curve from figure 6.12, and in a double reciprocal plot, we get a line out of that. And now what we're looking for, if we do all of the algebra, is to look to see where this line crosses the x-axis, the x-intercept. And then we can look at where it crosses the y-axis, the y-intercept. And if we do this, then we can read off the value of Km, because Km is simply going to be -1 over the value of the x-intercept, which in this case is -1 over -6.7, which comes out to about 0.15 millimolar. That's the substrate concentration, glucose in this case, at which our reaction is going at 1/2 of Km, or 1/2 of Vmax, I should say. We can also get Vmax from this plot, and for this we look at the y-intercept. So here Vmax is going to be 1 over the value of the y-intercept, which in this case is 1 divided by 0.1, or 10 micromole per minute. So that's the maximum velocity that this enzyme is churning out products starting with substrate. All right, so there's one more parameter of enzyme function that we can discuss, and your textbook discusses it. It's something called KCAT. KCAT is the turnover number. In other words, it's the number of reactant molecules that the enzyme can turn over per unit of time, let's say in 1 second. KCAT's directly related to Vmax in the following way. KCAT equals Vmax divided by the enzyme concentration. Its units are per second, and KCAT and Km are both intrinsic parameters of enzyme function. KCAT gives a sense for the intrinsic rate at which the enzyme can turn over reactants into products. Km is in essence a parameter that tells us something about the affinity of the enzyme for the reactants. There's a nice table in chapter 6 of your textbook that compares KCAT for a number of different enzymes that you might want to take a look at. All right, well, that concludes our discussion of quantitative analysis of enzyme function. I hope this discussion has been useful. Thanks for listening.